What's a field? Any field. Not like a hayfield. I don't mean like that kind of field, but a field in the context of physics, whether it be a gravitational field or an electric field or a light field or a heat field. What's a field? Kathleen, what's a field? Like an area, like a, yeah, right? Yeah, it's a line of influence that surrounds something. Now, we talk about gravitational fields. A gravitational field is a line of influence that surrounds a what? Good, an object with mass. That was a smart choice to pick that question to answer, wasn't it? Surrounds an object with mass. Good. Now, the Earth has mass. It has a lot of mass. It exerts a gravitational field. You have mass. You produce a gravitational field, although your field that you produce is a lot weaker than the Earth's field because you're much, much lighter than the Earth is. Let's draw a picture of the Earth or any other large object, large, heavy object. The gravitational field will always point towards that producer. It always points towards whatever it is that causes the field, the heavy mass. Notice the field lines, again, always pointing inwards here. If we put an object somewhere in this field, let's say this green ball again, somewhere in that field, what's going to happen to it? Oliver, it's going to go towards the Earth, right? It's going to go towards whatever it is that's producing it. Moves towards it, moves towards the Earth, moves towards whatever the producer is. What if I put an object over here? Where's it going to go? Yeah, it's going to go towards the Earth, right? Now, that's caused by the gravitational field, right? The force that's exerted on this object, the push or the pull that's exerted on this green ball is caused by the gravitational field, which is in turn caused by the Earth or whatever the producer is. What if I take this away? What if I take the experiencer away, the green ball away? There's no force anymore, right? A force is defined as what? A push or a pull. If we don't have a push or a pull, then we can't have a force. And we can't have a push or a pull unless there's something to be pushed or pulled. Now there's nothing to be pushed or pulled, so there's no force. Is there a field still? Yes. Still going to be a field because we still have the producer. We talk about gravitational fields to help us to see the effect, the influence of something, even if there's nothing to be pushed or pulled. The influence of the Earth is here. It's always there as long as the Earth has mass, even if there's no green ball to experience that influence, to experience that push or that pull. Does that make sense? Let's put the green ball back in there for a second. Okay, the green ball does experience a force downward now toward the Earth. There's two equations that we have now for gravitational fields. The first one we call the producer equation, Gm over r squared. The second one we call the experiencer equation, F over m. Both fields are valid all the time. Whenever we're talking about a gravitational field, both equations are valid. So how do we decide which one to use? Good. Whatever we have more information for. Whatever we have more givens for. This is the producer equation up here, the experiencer equation down here. If we know more about the producer, we're going to use this one. If we know more about the experiencer, we're going to use this one. What's the producer here, by the way? Is it the Earth or is it the green ball? Kevin? It's going to be the Earth. So if we know information about the Earth, let's use this one. If we know information about the green ball, let's use this one. What does M stand for there? What does M stand for there? Mass. Mass of what, Jazzy? Good. It's the mass of the producer. If we're talking about the producer equation, it's got to be the mass of the producer. And what does R stand for? It's a little bit of a tricky one, actually. What does R stand for? Justin, is your hand up there? Not always. No. Dustin said, isn't it the radius of the planet? It could be, but not always. It's the distance between the centers of the object. So if we're talking about the field strength out here where this green object is, then this would be our R, the distance from that object to the center of the Earth. Does that make sense? Now, if you're trying to find the field strength distance on the surface of that planet, then you're going to use the radius of the planet, right? If you're given this distance right here, then you would have to add the radius of the planet to that. All right? What's m stand for down here? Good. It's the mass of the ball, the mass of the experiencer, using the experiencer equation, right? F stands for the force experienced, the force felt by the experiencer. The force of what? Force of gravity that's experienced, right? Good. Is there ever a time when we can set these two equations equal to each other? Sure. If you're trying to find something about this and you know something about this, look, the field strength that's caused by the Earth right here is going to be the same as the field strength experienced by the green ball at that point. So there's no reason why you can't set them equal to each other. Sometimes it's not helpful to do that. Sometimes it is. If it is helpful, then go ahead and do it, as long as you're dealing with the field strength at that point. Now, the other thing you can do is go back to that equation that we learned before any of this, which was Newton's law of universal gravitation, gm1 m2 over r squared. If we combine this one and this one, then we end up getting this one anyways. Ends up being the same thing. All right? Okay, let's go to our next topic here. Our last topic of the unit, satellites and satellite motion. Who knows what a satellite is? How many people have satellite TV? Hands up if you got satellite TV. Where's the satellite on your house? Where's the satellite on your house, Kevin? On the roof? Where's the satellite on your house? Oh, so it's on top of the RV, okay. Trick question. The satellite is not on the roof of your house or on the roof of your RV. Satellite is not on the side of your house. The receiver is on the roof of your house. The satellite is what? A few people had their hand up when I asked them what a satellite was. Tom, what's a satellite? Yeah, the satellite is the thing that's orbiting around, not the thing that receives the signal from the satellite. The satellite is what transmits the television signal to your house, not what receives the television signal. A satellite is anything that orbits around something else due to gravity. Does that make sense? Now, we got a couple kinds of satellites. We have natural satellites and we have artificial satellites. A natural satellite might be something like the moon orbiting around the Earth, or the Earth orbiting around the sun. The Earth is a satellite of the sun. The moon is a satellite of the Earth. We don't usually talk about the Earth as being a satellite, but it is. Anything that orbits around something else in a gravitational field is a satellite. What about an artificial satellite? Well, same idea, something that orbits around something else, but this time it's something that we put there. So it's not the Earth orbiting around the sun, it's a communications satellite orbiting around the Earth, or the International Space Station orbiting around the Earth. We talked about this a little bit yesterday, I think. How high above us does the International Space Station orbit? About 400 kilometers, give or take a little bit, right? How fast does it travel? About 30,000 kilometers per hour, 400 kilometers above us. Boy, it could travel to us pretty quickly, right? Except it doesn't, because it would crash and burn up in the atmosphere if it was traveling towards us. But it would travel at 400 kilometers in a very, very, very quick time, going at 30,000 kilometers per hour. Anybody ever seen the International Space Station? It's actually not that hard to see, believe it or not. It's a pretty big object. Now, it's not, it's not the size of the moon or anything like that, nowhere close to that, but it's still a pretty big object. It's only 400 kilometers away. A big object 400 kilometers away, if you've got a clear sky, is not all that hard to find. Now, what do you see when you look up in the sky and see the space station? You don't see details of it. You don't see the astronaut looking out the window waving at you. Rather, you see a bright light. It's reflecting light from the sun, just like the moon's reflecting light from the sun. You don't see details of the moon either unless you use a telescope. You just see a bright light. Okay, the space station is the same thing. It's a bright light, but not as big as the moon. It will, however, be the brightest thing in the sky other than the moon itself. So how do you know where to look for it? Well, and computers are amazing now. NASA publishes a chart that tells you when the International Space Station is flying above you anytime. So in other words, we can look up right now, and we will in just a moment here, look up when the International Space Station will be above Okotoks next. Okay? Literally, all you have to do is go to NASA, the NASA website, and type in Okotoks, Alberta, and it'll tell us exactly when it's coming above us. So we look at this here, Thursday, May 22nd. Hey, that's today. At 3:13 a.m. this morning, it was visible for 2 minutes. It says a maximum height of 13 degrees. So that's not very high in the sky. That wouldn't have been a good sighting because it only happens for about 2 minutes, and it's only at 13 degrees above us. You'd like to see an angle of about 45 degrees or more, right? Because 45 degrees, if you kind of look up like this, you look up in the sky like this and see it nice and high in the sky at 45 degrees. Anything above that is even better because the higher it is in the sky, the easier it is to see. 13 degrees could get obscured by all the skyscrapers in downtown Okotoks or something like that, right? Gets obscured by trees and so on. Let's look for the next best sighting besides this morning. Oh, geez, there was one at 4:46 this morning that was really good, actually, for 5 minutes at 51 degrees. You would clearly see this thing going across the sky from the southwest all the way over to the east where the sun was going to rise in an hour or so. You missed that one, obviously. These are all AMs. Sometimes they're like 10:30, 11 o'clock PM, which is obviously a lot easier to be awake to see. Okay, look at that. Saturday, May 24th. If you happen to be awake at 4:45 a.m., go outside. Look at the west-southwest. That's going to be down there. West-southwest is down there. Okay, east is over here. 81 degrees. It's going to be very high in the sky, starting over there, coming around here, and then setting over there in the east. Okay, you will not miss it. You can't mistake it. It's a bright light going across the sky. You can't miss it. Okay? So here's your homework. Saturday, May 24th, get up at 4:41 a.m., go outside, and look up in the sky. Hopefully it's not cloudy so that you can see it. Look it up, guys, anytime. Like, listen, if you don't want to get up at 4:45 in the morning to watch a sighting, then look it up in a couple weeks. They'll be completely different, and you can and see where it's going above. So the space station is a satellite, an artificial satellite that orbits around the Earth. How does it stay in orbit around the Earth? What keeps it in orbit around the Earth? What keeps anything that's moving in a circle moving in a circle? Yep. Yes, that was my next question, actually. Even before that, though, what force always acts on an object when the object is moving in a circle? No matter whether it's the space station going around the Earth or the car going around eternally, it's the centripetal force. Now, what's that centripetal force caused by, Liam, in this case? It's caused by gravity. The centripetal force is caused by gravity in this case, right? It's a strong force of gravity between the Earth and the space station. Satellites travel more or less in circular orbits, although we know the Earth does go in a slightly elliptical orbit around the sun, pretty close to a circle, though, held in orbit by gravity. There's a centripetal force that's caused by a gravitational force. So when we had a car going around a turn way back in our last unit, or the first part of this unit, I should say, we said there was a centripetal force acting on that car between the tires and the road. And that centripetal force was caused by friction. So we set Fc equal to Ff, or mv squared equal to mu times the normal force, mu times m times g. Well, that's not what's keeping the Earth in orbit around the sun or the International Space Station in orbit around the Earth. It's gravity that keeps it in orbit. So instead of setting mv squared over r equal to mu times m times g, we're going to set Fc equal to the gravitational force. We're going to set mv squared over r equal to gm1 m2 over r squared. Now, good news and bad news here. The good news is we can simplify this equation a little bit and cancel some things out. The bad news is it's a little bit tricky to do that. First one, not so bad. You get an r over here and an r squared over here. One of the r's disappears on both sides. So it becomes mv squared equals gm1 m2 over r. We can also cancel out a mass. The trick, though, in this one is which mass is it that we cancel? Let's call m1 here the mass of the producer. So if we get the space station orbiting around the Earth, the producer would be the Earth. m2 we'll call the mass of the experiencer. Space station orbiting around the Earth, m2 would be the space station. If you're talking about the Earth orbiting around the Sun, then m1 would be the Sun, m2 would be the Earth. What m is this? On the left-hand side here, is that the mass of the producer or the experiencer? If we're talking about the space station orbiting around the Earth, are we talking about the mass of the space station, or are we talking about the mass of the Earth? Talking about the mass of the space station, it's always the mass of the satellite, okay, the experiencer. A lot of times when we use the equation mv squared over r, we don't even know what's causing the centripetal force. So how could we possibly use the mass of the producer if we don't even know what it is that's producing it? When we're using mv squared over r, m is always the mass of the experiencer. And when we're talking about satellite motion, the experiencer will be the satellite. So now we've got an me on both sides. Cancel it out. What are we left with here? On the left side, the only thing we've got left is v squared. On the right side, we've got g times m over r, m being the mass of the producer, the Earth, if it's the satellite orbiting the Earth, or the Sun, if it's the Earth revolving around the Sun. This equation does not appear on your data sheet, but this equation does, and this equation does. You just have to remember for a satellite, something orbiting around something else, you have to put those two equations together and solve for what you're looking for. Do your canceling and solve for what you're looking for. Here's an example. Earth's moon is 3.844 times 10 to the 5 kilometers. I want to circle that because I don't want to be in kilometers from the Earth. Now, that means, they don't say this, but that means from the center of the Earth to the moon. If you look at the diagram, you can see that, right? From the center of the Earth to the center of the moon, 3.844 times 10 to the 5 kilometers. What's the orbital speed of the moon? In other words, how fast is the moon moving? How fast is the moon moving at any given time? Well, we know that we can set Fc equal to Fg. We've got a satellite. Satellites are held in place by gravity. The centripetal force will be equal to that force of gravity. One of the r's cancels. One of the m's cancels. The mass that I'm left with is the mass of the producer. So it becomes v squared is equal to g times the mass of, in this case, the mass of the Earth over r. We want to find v? We're going to square root all that. G times me over r. Let's get the number now. Before we do, actually, make a prediction. I want you to write down how fast you think the moon is moving. Before you do a calculation, just write it down on your piece of paper. Okay, I don't care if you're wrong. I just want you to predict how fast you think it's going to be moving. Okay, and write down a number. Commit to it. And write down a number on your paper. The mass of the Earth is 5.97 times 10 to the 24. And divide that by r, 3.844 times 10 to the what? 10 to the what? What is it? Good. Thank you, Austin. 10 to the 8 meters. Do you have to square that? No, the squared canceled a minute ago here. So here's what we got now. Let's pull out the calculator and solve it. Say 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24. Let's divide that by 3.844. times 10 to the 8. And then finally, let's square root that. And we get 1017. 1.02 times 10 to the 3. So how fast is the moon moving at any given time? Almost 4,000 kilometers per hour. That's pretty fast. 4,000 kilometers per hour. People have stood on the moon when it's moving 4,000 kilometers per hour. Is that a problem? No. As long as they're moving at 4,000 kilometers per hour as well, then it's not a problem, right? We're moving pretty fast on the Earth as well if you actually did the calculation. Okay, let's try these two sample problems, please. On page 278. Let's take a look at number 2 here. It says the moon, Miranda orbits Uranus at a speed of 6.68 times 10 to the 3 meters per second, 6,600 meters per second. Use this speed and the mass of Uranus to determine the radius of Miranda's orbit. The mass is 8.68 times 10 to the 25 kilograms. All right. So the moon, Miranda, is the satellite here. It's the thing that's orbiting around the planet. We know that when we have a satellite, there's a centripetal force. And we know that centripetal force is caused by the force of gravity. So let's set mv squared over r equal to g m1 m2 over r squared. One of the r's on each side cancels. So it's gone off of the left side. Now we've got 1 r left on the right side. We've got one mass canceling as well. The mass that's left is the mass of what? The mass of the producer. In this case, it would be the planet. Or is it the mass of the moon? What's left over here? What's left over here, Kathleen? Good, the mass of the producer. So we've got v squared is equal to g times the mass of the planet, Uranus, divided by r. V is equal to, what are we looking for here? We're looking for r, right? So let's rearrange this to solve for r. The r goes up by multiplying, the v squared goes down by dividing. It becomes g times m over v squared. 6.67 times 10 to the minus 11 times, use the right mass here. The mass of the planet, 8.68 times 10 to the 25. And we're going to divide that by v squared. 6.68, yeah, 6.68 times 10 to the 3. Watch how I enter this into my calculator. Okay, watch how I enter this into my calculator. Some of you guys like to, when you're putting an exponent in, say something like this, 6.68 times 10 to the 3, and then square that. Don't do that. Okay, don't do that, especially when the number you're trying to put in scientific notation is on the bottom. Okay, do this. 6.68 times 10 to the 3. And then you can square that number just like that. Whoops. Don't multiply by 2. Square it. Okay, square it. And then you get your number there. Okay? So let's try this. Let's go 6.67 times 10 to the minus 11. Let's multiply that by 8.68 times 10 to the 25. Let's get a number on the top. And now let's divide that by 6.68 times 10 to the 3 squared. What do we get? 1297, 1.30 times 10 to the 8 meters. Guys, does that make sense?
Yeah, I didn't do I didn't use the E.
Okay. So you went times 10 to the whatever, like the first way I showed you, yeah. Yeah, you know what? 8 times out of 10, probably 80% of the time, if you use that first way of plugging it into the calculator that I showed you, it's going to work. But 80% of the time isn't good enough, right? We want 100% of the time, especially when it's on the bottom. Okay, use the EE button. That's what it's there for. Okay, when they built your calculator, they meant for you, when you were putting in something in scientific notation, to do this. right? Not the way that I showed you the first time. Okay, so use that EE button. All right, let's take a look at another example here. So it says Landsat is an Earth imaging satellite that takes pictures of the Earth's ozone layer and geological features. It orbits the Earth at a height of 912 kilometers. What's the orbital speed and the period? The orbital period. It's a satellite. In a satellite, we say that FC equals FG, or mv squared over r equals gm1 m2 over r squared. R cancels, one of the m cancels. We're left with v squared is equal to g times the mass of the Earth, in this case, divided by r. We want to find the speed. Well, that's easy enough. V is equal to the square root of g times the mass of the Earth over r. The mass of the Earth is 5.97 times 10 to the 24. And what r do we use there? 912? What r do we use? What r do we use? Devin, what r do we use? Jeff, what r are we going to use there? 912? Good. Let's convert it to meters, and let's use that plus the radius of the Earth. 912,000 plus, you don't have to memorize this number. You can always check on your data sheet for this. 6.38 times 10 to the 6, the radius of the Earth. Jeff, why did you add those two numbers together? Good. It always comes from the center. You always have to measure that distance from the center. Let's not forget to square root that. Okay, let's do this one on the calculator as well to make sure that you guys can handle that. Go 6.67. We won't worry about the square root right now. 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24. Let's divide that by, now watch really carefully here. Use some brackets, 912,000 plus 6.38 times 10 to the 6. Let's end that bracket, and now let's, no, we don't square r, do we? We don't have to square r there. Just about to square that. Let's press equals. Now let's square root that. What did I just do? That's better. 7185.7. Or 7.19 times 10 to the 3 meters per second. All right, good. There's the speed. Here's the million-dollar question. What's the period? In other words, talking about the period of the Earth revolving around the sun is 1 year. That's how we define a year, how long it takes for the Earth to go around the sun. What's a year worth for the Landsat satellite? How long does it take to do its revolution? What's a Landsat year? The period of revolution. Dustin, you want to take a try at that? Yes, that's exactly it. Dustin said it's the circumference divided by how fast it's traveling. In other words, v is equal to 2 pi r over t. We're going to take that and rearrange it. We get 2 pi r over v. 2 times pi times the radius was 912,000 plus 6.38 times 10 to the 6. Okay, we're always going from the center of the object, center of the producer, divided by v, 7185.7. So let's say 2 times pi times, let's do some brackets here, 912 plus 6.38 times 10 to the 6. Now let's divide all that by the answer that we just got, 7185 meters per second. And you get 6,376. Good. 6,376 seconds. So basically, it's a couple of hours. That's the period of it, right? A couple of hours. Is that good? All right. Let's try these guys then. Page 279, question 1 and 2.